Every 26 months, the Earth approaches a close point with Mars. This is the logical time to launch probes to the red planet. For a brief period in mid-2020, a launch window opened. The Europeans, in collaboration with Russia, had planned an ExoMars rover mission, but problems with the descent stage and its parachute meant the mission would be delayed for a further 2 years. The first mission to launch toward Mars was from a new entrant into the space business. The UAE, in collaboration with the University of Colorado at Boulder, built an orbiter which was launched on a Japanese H-2A rocket from the Tanegashima Launch Center. China was also keen to launch its first independent mission to Mars. The country's only other attempt at Mars exploration was in 2011 as part of a Russian mission that failed to leave Earth orbit. The Tianwen-1 mission carries an orbiter, a lander, and a rover. The most ambitious Mars mission to launch in 2020 was NASA's Perseverance rover. NASA's Jet Propulsion Laboratory has been designing and building spacecraft since the earliest days of space exploration. In 1997, JPL's Pathfinder mission used an airbag system to deliver the Carl Sagan lander to the plain of Ares Vallis in Mars' northern hemisphere. The lander was essentially a weather station with a stereoscopic camera, but it carried a technology demonstrator, Sojourner, which became the first vehicle to traverse the surface of Mars. It found evidence that in past eons, water had once been plentiful on the surface of the red planet. It appeared that Mars had once been a very different place. In 2004, JPL's twin Mars exploration rovers, Spirit and Opportunity, landed in opposite hemispheres. These were much heavier vehicles, yet the bounce landing technique still worked well. Both had been targeted at craters that appeared to have been lakes in the distant past. The two solar-powered rovers had been designed to operate for a period of 90 days. 10 years after they landed. Although the rovers had sustained damage, they were both still functioning. Again, they discovered water had been abundant and had left distinct patterns of streams and rivers. Clearly, Mars had been much warmer. With large areas of standing water, it must have had a thicker atmosphere. Astrobiologists began to wonder if the planet could once have been a home to life. Next, JPL began preparation for a more ambitious Mars mission using a much larger rover for launch in 2012. The Mars Science Laboratory, ultimately called Curiosity, was almost 1,000 times heavier than Sojourner. And it did not have to rely on solar panels, it carried a radioisotope power source.
5, 4, 3, 2, 1... fire.
A new landing system was developed as Curiosity's weight was too great for the previously used airbag technology. Curiosity continued the accumulation of knowledge about the role of water in Mars' ancient past. With each stage of Mars exploration, researchers began focusing on the idea that it might be possible to find traces of past microbial life. Perseverance is JPL's latest rover. Its basic design and its landing system are very similar to Curiosity, but there have been some important refinements to its scientific payload and to its objectives. Its instruments will match chemically promising rocks with an analysis of the patterns within the sample structure that may hold clues to past microbial development. Like its predecessor Curiosity, the new rover has a robotic arm fitted with drilling tools and sample analysis instruments.
In terms of robots that go into space, the sampling and caching system on the Mars 2020 mission is the most complicated, most sophisticated thing that we know how to build. This is the system that allows us to take core samples of rocky material on the surface of Mars, carefully seal them in very sterile, clean vessels for eventual return to Earth.
In 2027, a joint NASA-ESA mission will land near Perseverance. A European rover called Fetch will collect all the sample tubes. This is a much lighter rover than Perseverance and is powered by solar panels. It can travel at 10 times the speed of the larger rover, and it must be able to navigate accurately to the areas where the sample tubes have been left. Fetch will deliver the samples to a NASA-built lander. This includes a small, solid-fueled rocket that will take the samples to orbit. The sample tubes, now contained in a capsule, transfer to a waiting European orbiter. This craft has the ability to wait in Mars orbit indefinitely, should there be some unforeseen delay on the ground. The return craft, built by Airbus, features ion propulsion that has huge weight and cost benefits to the mission. As it nears the Earth, the spacecraft releases a re-entry capsule that will land in the United States sometime in the early 2030s. As the samples are robust, the capsule does without a parachute system. With a limited amount of space available for specimens, it is crucial that the samples selected are finely targeted toward the detection of biosignatures, the mission's primary focus. Inside the rover, a second robotic arm receives the sample. Its volume is measured, the sampling tube is sealed, and then it is stored, with each stage being photographed. Perseverance will not select samples autonomously. Images relayed to Earth will help scientists decide which specimens to collect. So that the astrobiologists understand what to look for, a NASA-ESA field trip to the remote regions of Western Australia was organised. It's here that the oldest convincing fossilised remains of microbial life can be seen.
This is one of the most important places on the planet, geologically speaking. The rocks you see right in front of me here, these wrinkly layered structures that we call stromatolites. Structures like this actually represent fossilized microbial mats, basically fossilized pond scum in a sense. Microbes, bacteria living in a shallow water environment, and we believe that if life ever existed on Mars, it would have been purely microbial. When we say with Mars 2020 we're seeking the signs of ancient life on Mars, this is precisely the kinds of signs of life that we'll be seeking.
But mission planners had to decide where the most likely area of Mars to search for these biosignatures would be. Selecting the Perseverance landing site was an exhaustive process that relied upon the detailed survey work carried out by the Mars Reconnaissance Orbiter, the MRO, which began mapping Mars in 2006. Since then, it has returned the most detailed images of Martian topography.
This has been one of our major discoveries, is the variety of environments, of water environments, that occurred very early in Mars history. We think that gives Mars a much better chance, for instance, to be not only a habitable place, but a place that might actually, where life might have gotten a start, because there were many choices of environments that could help support it.
Several landing sites were promising, but in 2018, Jezero Crater, just 17 degrees above the Martian equator, was chosen. It contains a 20-kilometer open, flat area, ideal as a landing zone. It appears to have once been a lake with a delta region where an inflowing river dumped its sediment. The crater rim is rich in clay-like minerals. On Earth, clays tend to concentrate and preserve organic materials. But landing within Jezero Crater presented new challenges. In an hour across easy ground, Perseverance will cover around 152 meters. So inaccuracies in landing could cost the rover as much as 12 months in driving time. While Perseverance looks similar to its predecessor, Curiosity, it is heavier, which meant designers had to completely rethink the spacecraft's landing technology. Since the Viking landings in 1976, all Mars craft had used variations of a supersonic parachute designed in 1972. The Martian atmosphere is far thinner than Earth's, and any craft is still traveling at supersonic speeds after the scorching entry. Previous parachutes had been tested in the supersonic wind tunnel at NASA's Ames Research Center, but with the extra weight of Perseverance, the wind tunnel was just not big enough. Not since the big budgets of the 60s and 70s had NASA tested in the Earth's thin upper atmosphere. But with a parachute more than 21 meters in diameter, there was no other way. A two-stage Black Brant 9 sounding rocket lifted the payload and parachute to a height of 50 kilometers, where they separated and began falling back to the ground. In the Martian atmosphere, the parachute will release 11 kilometers above the surface. The density of the Earth's atmosphere is of a similar thickness at 37 kilometers, which is the height at which the test parachute was deployed. A parachute is the most economical way of slowing the craft down. The developers continued with the ring gap band design, known for its stability, monitoring the behavior of the three variants being tested. There were mixed results. Ultra-high-speed photography was used as designs were exposed to forces exceeding the worst expected at Mars by 40%. Perseverance has 3 cameras looking up to record its parachute's deployment. Unlike previous Mars missions that saw the parachute deploy at a predetermined speed, Perseverance is equipped with a range trigger that will release the parachute according to its position relative to its landing target. This will increase landing accuracy by 50%. When the landing craft breaks free of its parachute, another landing aid, called the Terrain Relative Navigation System, will already have compared camera vision to its internal map to fine-tune the targeting. To fine-tune the Terrain Relative Navigation System, members of the Entry, Descent and Landing Team went to Death Valley in California's Mojave Preserve. The area was selected because of certain similarities it has with the Jezero Crater region. An Airbus H-125 helicopter was fitted with the lander's vision system. The first task was to plot the Death Valley region so the system had an internal map to work with. A trailer served as the monitoring center. The team here could see how well the system matched its internal map with what its cameras saw. The first images made by the navigation system are from a 4-kilometer altitude as soon as the heat shield is jettisoned. After it has made 15 landmark matches, it changes to a higher resolution to refine its path toward the desired landing location. Alan Chen is lead engineer for Mars 2020's cruise phase and for the craft's entry, descent and landing phase, and he held similar roles for the previous Curiosity mission.
Part of the guided entry, what that allows us to do finally is land in a safe spot next to some of the dangerous stuff that people want to go look for science in, and actually be able to drive there. Our driving capability of the rover, because it's beefed up and we have a fairly long lifetime, is on par with the landing error uncertainty, how far we're going to miss the target or miss the desired science target. So we can, at this point, go to places on Mars and say, we want to go there, we'll land next to there and drive there.
Jezero Crater was rejected as a target for the Curiosity mission because the landing constraints were too tight. Terrain relative navigation raises the probability of an accurate landing from 85% on the previous mission to 99% with Perseverance. Mars is not like Earth. While images of the surface of Mars can bear striking resemblance to arid deserts here, the temperatures Perseverance will meet during the course of a Martian summer day range from highs of 20 degrees Celsius to lows of minus 78 degrees Celsius. While analogues on Earth can be helpful to researchers looking for signs of life, there are some aspects of the mission for which engineers had to draw upon previous Mars experience. While the Perseverance rover is built to the same template as Curiosity, there were improvements the development team knew they could make. Periodically, the Curiosity rover uses the Marley camera on its robotic arm to record a self-portrait. The camera is designed to capture close images of rocks and has a reasonably narrow angle of view. But by taking a precisely aligned series of 84 separate images, staff on the ground can build up a complete picture of the rover. The very similar Watson camera on Perseverance has already started performing the same task. From such pictures, the Curiosity team realized that, in its first year of operation, its wheels were sustaining damage. The extremely low temperatures on Mars rules out rubber as a form of traction. Designers opted for a machined aluminium wheel with raised ridges called grousers. For Perseverance, the wheels have been made with a slightly greater diameter, yet they are slightly narrower and with a different pattern in the grousers. While the rover can only travel 152 meters in an hour, its advanced navigation system will have it covering twice the ground that Curiosity could traverse, meaning that the new wheel design will have to take greater punishment. Perseverance can handle surfaces that slope 45 degrees in any direction, though drivers will not negotiate anything in excess of 30 degrees. All rovers made at JPL have been built with a rocker and bogie suspension system that allows the wheels to rise over obstacles while keeping the weight evenly distributed. Each wheel has its own drive motor, and the front and back wheels are steerable, enabling Perseverance to turn 360 degrees on the spot. For science and to monitor the health and behavior of the rover, Perseverance has a total of 23 cameras. The most prominent of these are in the rover's elevated mast. The single large-diameter SuperCam, a science instrument that combines a camera with a laser, can vaporize a tiny area of a rock from as far away as 7 meters and analyze its composition using spectroscopy. Beneath the SuperCam are 4 cameras that work in stereo pairs. The 2 outer units are of fixed focal length and function as navigation cameras. They're important when Perseverance drives autonomously. 2 more cameras with square lens hoods are known as the Mastcam Z, that Z meaning they have zoom lenses. These are the primary eyes of Perseverance. They can capture high-resolution images in 3D, and they can record video at 4 frames a second. They will also be used for looking up at the atmosphere and in the positioning of the robotic arm. To protect its cameras from airborne dust during the nights, the mast folds down into its transit position. The Watson camera, mentioned earlier, has a primary function of capturing close detail of rock types, but its position on the robotic arm gives it great versatility. It is the only way engineers have of seeing the underparts of the rover, and at full stretch it has a higher viewpoint than the mast cameras. In self-portraits, the arm cannot see itself and appears to be missing from the final image. Other cameras closer to the ground are used for hazard detection, with 4 at the front and 2 at the rear. The aeroshell that protects the rover during the cruise phase and through entry and descent has 3 cameras looking up to observe the unfurling of the parachute. Another camera on the rocket-powered descent stage records the separation and lowering of the rover to the surface, with a further camera beneath the rover looking down at the surface. Perseverance's cameras, along with all the information collected by the science instruments and the engineering systems, generate a lot of data. For data storage, the rover's computers have 2 gigabytes of flash memory, hardened to tolerate extremes of radiation. Though this may seem small, the limiting factor is the speed at which Perseverance can send the data to Earth. The fastest link is with the ultra-high frequency antenna via the Mars Reconnaissance Orbiter. Though it was launched in 2005, the MRO remains the most advanced telecommunications platform in deep space, but its backup amplifier has failed. The orbiter has 20 gigabytes of flash memory, and with its 3-meter dish, it can relay data to Earth at 6 megabits per second, much faster than its UHF link with Perseverance that transmits at a maximum 2 megabits per second. The rover also has high-gain and low-gain X-band antennas that can communicate directly with Earth, but at much lower data rates. Mars Odyssey, in orbit since 2001, can also act as a relay satellite, but it's aging. Modern craft on the surface of Mars generate data faster than the relay satellites can return it to Earth. Europe's Mars Express can relay signals from the surface to Earth, but it too is getting old. NASA has made studies into a new generation of Mars communication satellites, but this remains a weak link in the agency's plan for a manned expedition to the Red Planet. Across the rover, 6 sets of sensors monitor air temperature and pressure, humidity, solar and cosmic radiation, as well as dust. Collectively known as MEDA, its job is to record variation in the environmental factors that affect life, not just ancient microbial life, but human life. NASA makes no secret of its ambition to send astronauts to Mars, perhaps in the 2030s, and part of Perseverance's brief is to explore habitability. The agency is committed to a series of moon landings in this decade and has been working on an expedition spacesuit that will also be used at Mars. But there are still questions to answer. Life on our planet is protected from both solar and cosmic radiation by the Earth's magnetic field and by the thickness of the atmosphere. The surface of Mars has far less protection, At some point, Mars' magnetic field died, allowing the solar wind to gradually strip away the atmosphere. Humans on Mars will have to limit their exposure to sources of radiation. At the front of the rover, samples of the different materials from which NASA makes spacesuits are attached as part of the calibration target for the Sherlock instrument. Spacesuit designers are keen to observe any changes during prolonged exposure to the Martian environment. The Sherlock instrument, mounted on the rover's arm, uses a laser, spectrometers, and a camera to make detailed analyses of geological samples. The instrument was calibrated on the ground, but it is regularly checked against known samples on the calibration target. As well as the 5 spacesuit materials, the samples include a slice of Martian meteorite and a sapphire disk. A different unit, called MOXIE, is also looking toward a manned landing on Mars. MOXIE is a demonstration technology that uses solid oxide electrolysis to separate oxygen from Mars' CO2 atmosphere. Essentially, NASA is sending an oxygen factory to Mars. The unit draws a very substantial 300 watts, which is why it will only operate for around an hour every few months. NASA obviously feels that MOXIE's huge power drain, combined with its 17-kilogram mass, is worth taking to Mars. Making the huge volumes of oxygen for a manned mission to Mars will be far cheaper and less complicated than carrying it. And MOXIE is an important first step in testing the technology where it's needed. Perseverance carries another technology demonstrator, a small helicopter known as Ingenuity. It will stay tucked beneath Perseverance for 2 months, while the rover seeks a large flat area suitable for test flights. Building a drone to work under Martian conditions was not easy. While the planet's gravitation is roughly 1/3 of the Earth's, the thin atmosphere that limits the effects of the landing parachute also makes it hard to fly. All flight tests were carried out in JPL's 8-meter vacuum chamber under simulated Martian conditions.
The first and foremost challenge is to make a vehicle that's light enough. And then the second is to generate lift. The rotor system has to spin very fast. 2,000, 2,200, 2,400, 2,600. It's that balance of a very light system coming under 2 kilograms. In fact, we weighed in under 1.8 kilograms. We have to be light to fly at Mars.
Ingenuity has to function autonomously. Flight instructions will be sent to it via Perseverance, and at the end of each brief flight, the rotorcraft will relay performance data back to the rover for relay to Earth. All simulations went according to plan. Though the team has every confidence in the craft's flying qualities, an extra level of complexity was involved in stowing the helicopter for transit and for safely separating it from the rover onto the surface of Mars. At the appropriate time, the protective carbon fiber shield beneath the rover will be jettisoned, and the rover backs away to leave clear space. The transit latch is released, and the helicopter's electrical connection to the rover is severed. Then it's brought into an upright position. This mundane deployment must be flawless. Any glitches could render both the helicopter and the rover useless.
2, 1, 0.
The Ingenuity team has an experimental window of 30 Martian days. 5 flights are planned for this period. As a safety margin, Perseverance will back away 100 meters before the helicopter attempts its first flight. This is scheduled for late morning. The craft should have warmed after the bitter Martian night, and yet the atmosphere should still be cold and slightly more dense, which will assist with the lift. The first flight will be straight up to around 3 meters with a brief hover period, followed by a prompt return to the surface.
It has to be fully autonomous from the time it takes off to the time it lands. What we do on the ground is we plan the flights, and so we determine from here where we want the helicopter to go.
The information gathered by Ingenuity is solely related to its performance. Future Mars missions will benefit from the flight experience accumulated by the rotorcraft. After each flight, Ingenuity's solar panel requires a full Martian day to recharge its 6 lithium-ion batteries. 2/3 of the charge is used to keep electronics warm during the Martian night.
Most of our flights will be at the 3 to 5 meter height. We will be going horizontally again at a few meters per second, probably go out, 50, 70 meters and come back. In successive flights, we'll probably push that further, try to go further. So our priority will be to get back engineering telemetry and not so much images, but I'm sure we'll return a few, because they'll always look cool.
A black and white navigation camera and a higher resolution color camera are the only instruments on the craft. The Wasatch Range and the dry Walker Lake in Nevada. Here, a team of 7 mission specialists and their instruments were standing in for Perseverance. Even before the mission had been launched, planetary geologists were able to gain experience in using the rover. In locations around the world, 150 scientists were monitoring the instruments in an exercise called Rover Operations Activities for Science Team Training. Over a period of 2 weeks, the science teams were practicing how to interpret what they saw and issuing instructions to the mission specialists about what they want to investigate further. The rover's Mastcam Z and its adjacent color navigation cameras were represented by a cluster of conventional digital cameras. The main investigation team initially requested a 360-degree panorama, but they soon realized this would generate 10 times more data than could be transmitted in one day. A more modest plan soon emerged for a low-resolution mosaic of the bank in front of the rover. A wheel-mounted frame housed a ground-penetrating radar unit that imitated Perseverance's RIMFAX subsurface experiment. A handheld X-ray analyzer to determine rock chemistry stood in for the rover's pixel experiment.
It's best so that I can grab it out.
Using just the information relayed to them by these instruments, the science team name specific features and formulate plans for further investigation, plotting moves for the rover to make for the next day's observations.
For what the end of drive should look like. It looks like it's just a rotation, and that's the box where the wheels would fit in.
The science teams that drive the investigation are reliant upon the engineering team that drives the rover, and learning how to operate together smoothly is an important part of the training.
We don't need to be higher fidelity than that.
In February 2020, the engineers at JPL in California, who had hand-built Perseverance, began methodically packing their work into transit cases for its journey to the Kennedy Space Center in Florida. The rover, its rocket-powered descent stage, and the cruise stage that will protect it during its voyage to Mars would be integrated at the launch site. But one vital component, the power source, had not yet seen the rover. Perseverance is designed to work with the multi-mission radioisotope thermoelectric generator. It had been built for NASA by the US Department of Energy at the Idaho National Laboratory. Inside the unit, 8 pellets of plutonium-238 dioxide glow with a red heat thanks to radioactive decay. Thermocouples clustered around these pellets convert the heat to electricity. Because there are no moving parts, the system is very reliable, but the conversion rate is inefficient. Some of the excess heat is tapped off to directly heat the rover. Remaining heat dissipates via 8 cooling fins. In April 2020, the unit, housed in a specially cooled protective cask, arrived at the Kennedy Space Center. At the start of the mission, the plutonium generates about 2 kilowatts of thermal power, which is converted to 125 watts of electrical power. After 14 years of operation, this will dwindle to 100 watts of electricity. Soon after its arrival at the launch center, the power unit was briefly connected to the rover for a fit check. Because of the heat it generates, it would not be reconnected until the rover was on the launch pad. During testing, the rover was fitted with a dummy power supply without its plutonium heat source. At various stages of the build, the rover and its spacecraft were put through punishing examinations. Vibration and high-volume sound tests subjected the craft to conditions it would experience during launch. The rover was exposed to extremes of heat and cold greater than could be expected on the surface of Mars. At various stages during its construction, and particularly in the final few months before launch, the major components were weighed and spin tested to determine the distribution of weight across the configuration. Because the craft rotates during its cruise phase, balance is important. And just as a car's wheels are tested for balance and corrected with weights, so too are spacecraft balanced. Balance of the rover separate from its delivery system is also important, particularly as it is lowered from its descent stage to the Martian surface. The rover's chassis had slightly more than 6 kilograms in supplementary weights added to bring its center of gravity to within fractions of a millimeter of its design specification. Other weights in the back shell will be jettisoned just before entry into the Martian atmosphere. Throughout the building and testing of Perseverance and its spacecraft, all staff wore cleanroom suits, affectionately known as bunny suits. They protect the electronics and precision engineering from contamination. A hair or even a flake of skin can cause serious difficulties if it gets into the wrong place. Because this mission is searching for evidence of life, it is crucial that all components are not just free of particulate contamination, they must be sterile. The Planetary protection team regularly swabbed surfaces and tested for bacterial spores to verify that the craft could not contaminate the Martian environment. Panels on the spacecraft are regularly wiped with alcohol, while parts that cannot be cleaned this way, like the central processors, are sealed behind a microbial filtration system. Other components, like the parachute, were sterilized by prolonged exposure to high temperatures. The required standard says the rover and its spacecraft should carry fewer than 500,000 bacterial spores. Given how small these spores are, this is a very limited number. It was after the 1969 Apollo 12 landing on the Moon that NASA realized biological contamination would be a problem.
There it is! Son of a gun! Right down the middle of the road! Outstanding. 42 degrees, Pete. Hang in there. 30 seconds. 18 feet. Coming down at 2. He's got it made. Come on in there. 24 feet. Contact light. Roger. Copy contact.
The lunar module touched down within walking distance of the Surveyor 3 spacecraft that had landed in 1967. Engineers wanted to understand what prolonged exposure to space did to their hardware. So the astronauts returned to Earth with several pieces of the surveyor, including its camera. Subsequent analysis revealed the presence of the common bacterium Streptococcus mitis on the camera. While moon rock examinations were scrupulous, the hardware tests were not. To this day, it remains unclear whether the spores had survived on the moon for more than 2 years, or if the parts had been contaminated after their return to Earth. The rover's sample acquisition hardware received special attention to guarantee the integrity of the material collected on Mars. The rover carries 39 sample tubes and 5 witness tubes. Standards here far exceed those for the rover and spacecraft generally. Organic compounds inside the tubes must be less than 1 part per billion. When it's needed, a fresh sample tube is inserted behind the hollow drill at the end of the rover's robotic arm. The drill penetrates to a depth of around 5 centimeters, and its core sample weighs about 15 grams. After the percussive drilling, the core sample inside the tube is snapped off. Inside the rover, the sample is handled by a second robotic arm. Before the tube is sealed, it is weighed and then photographed. Staff at JPL hit a major snag when preparing the sample tubes. The intention had been to subject the tubes to sustained temperatures. While this sterilized them, their surface was subtly changed, causing a loss of smoothness leading to problems with the sealing system. Ultimately, a combination of heating, rinsing with solvents, and ultrasonics gave the required results. The sample tubes were one of the last items fitted to the rover. Since the outbreak of the COVID-19 virus, there has been a third, completely new reason for engineers and technicians to wear masks. JPL's site in Pasadena has seen stringent viral protocols implemented, with those who can working from home. A narrow launch window meant work on the rover could not slacken, though it was made more complex by the pandemic. In June 2020, it was decided that a plate should be affixed to Perseverance to acknowledge the challenging work carried out by frontline medical workers. Even the staff and serpent was swabbed to test for bacterial spores. The plate is intended to remind future explorers of the year 2020 and the global pandemic. An Antonov 124 landing at Cape Canaveral's skid strip runway. It carried the Atlas V launcher that would send Perseverance to Mars. It's May 2020, and as the launch window approached, components of the Mars 2020 mission were delivered to the Kennedy Space Center. Most of the rover and its spacecraft had arrived at the Cape several months earlier, where it had been unpacked and thoroughly checked. But final assembly could not begin until the sample acquisition system was delivered, also in May. The Atlas V core stage and its boosters were conveyed to the ULA Vertical Integration Facility, known as the VIF, adjacent to Cape Canaveral Launch Complex 41. Here, the components are raised to the vertical and bolted together. It is interesting that while Russia was unable to meet its launch commitments for the European ExoMars mission, Its dual-nozzle RD-180 engine is providing the primary first-stage thrust for Mars 2020. Atlas rockets have been using the reliable and very efficient Russian engine since 2000. But US political considerations are pressing the United Launch Alliance to develop an American replacement. For the Mars mission, the Atlas V was configured with 4 solid propellant boosters. Made by Aerojet Rocketdyne, these boosters have fixed engine bells, so the Atlas V is completely reliant upon its core engine for directional control. At the Kennedy Space Center's Payload Hazardous Servicing Facility, the rover and its descent stage were united, then sealed inside the back shell and the heat shield. Other elements of the cruise stage, including the disk of solar panels, were attached before the complete spacecraft was sealed inside the payload fairing and readied for transport to the launcher. In June, the Centaur upper stage arrived at the VIF. This would propel the Mars 2020 craft beyond Earth orbit. The thin skin of the Centaur relies upon the pressure of its liquid fuel to keep it stable. While empty, the Centaur is filled with pressurized nitrogen to prevent it collapsing. In early July, the spacecraft and its fairing arrived for integration with the now complete Atlas V. There remained several weeks before the commencement of the launch window. From July the 30th to August the 15th, there would be roughly a 3-hour period in the Florida mornings in which the Mars 2020 mission could be launched. Any technical setbacks at this late stage could see the launch delayed for 26 months. However, there was one crucial piece of hardware still to be fitted. Months earlier, when the VIF was still empty, a special test run had been staged. Perseverance's power supply is mission critical, but it's hard to manage. While the RTG is radioactive, at this early stage of its nuclear decay, the overwhelming portion of its emissions are alpha particles that have difficulty penetrating a sheet of paper. They can easily be shielded. The problem with the plutonium power source is the huge amount of heat it constantly radiates. Sealing it in a confined fairing without some way of dissipating this heat would damage the spacecraft. Only after the rocket has been erected with its payload in position can the power plant be connected. Technicians gain access through hatches in both the payload shroud and the rover's back shell. At all times, the RTG is cooled by a heat rejection system that remains functional until cooling loops within the rover take over the task. Two days before the launch window opened, the Atlas V began its move from the VIF to Space Launch Complex 41. Feed lines were attached and the upper and lower stages began taking fuel and oxidizer. On the morning of July the 30th, the countdown reached its final moments.
Engine ignition, 2, 1, 0. Relay and liftoff. As the countdown to Mars continues, the perseverance of humanity launching the next generation of robotic explorers to the Red Planet.
The launch was perfect. The Centaur upper stage fired for its second time to push the cruise stage out of Earth orbit toward Mars. At this time, both the cruise stage and the Centaur were on a path that would see them miss the Red Planet. Several weeks after separation, a course correction brought Perseverance onto the correct line, leaving the upper stage to follow a path that would see it orbit the Sun. During its 6-month cruise to Mars, several more course refinements ensured the craft would arrive at Mars on February the 18th, 2021. When the landing day arrived, team members at JPL were intently watching their consoles. At this point, any signals sent to the Perseverance craft would take 11 minutes. So the precise sequence of landing instructions had to come from the craft itself.
Standing by for cruise stage separation.
Cruise stage sep.
We have confirmation of entry interface.
At the top of the atmosphere, the craft was traveling at 19,000 kilometers per hour. Its thrusters were keeping it positioned blunt end first, with the heat shield protecting the rover from the extreme temperatures.
We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground. The navigation has confirmed that the parachute has deployed and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance is now slowed to subsonic speeds and the heat shield has been separated.
Perseverance's high-definition cameras began recording various aspects of the landing procedure. They could recognize surface features, and the craft began plotting a course for Jezero Crater. Soon, the rover, cradled in the rocket-powered descent stage, broke free from the back shell and parachute. When it was close enough to the surface and kicking up dust, the sky crane began lowering Perseverance gently to the ground. This was the first time a spacecraft had recorded its own landing.
Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
NASA had landed the most sophisticated rover yet built at a precise location in Jezero Crater. Its investigations will continue for at least 10 years.